logic to create whatever type of tree you want. Okay, so tree creation logic can be replaced afterwards, and the traversal methods will remain same. Okay. So here in our first assignment, we want to create the expression tree from postfix or prefix expression. So today we will discuss that function. Okay. The example of which is already discussed in the lecture. Okay. But if you want, I will just go through that example, and after we see the logic, we can again go through that example and check whether it is working fine or not. Okay. So here we have to create the expression tree from prefix or postfix expression. So any of this is input, prefix expression string or postfix expression string. And from that you have to perform recursive and non-recursive traversal. After creation of the tree, traverse it using all the traversal methods. Here again in this we have declared a class node in the similar way. Data is in character, because now in the expression we will have operands or operators which are characters. That's why character data is there in the node and left right. Okay, and this is parameterized constructor in the same way. Data equal to x, left right is node class. Then we'll need this stack class for the non-recursive traversals afterwards, and class tree is there. Okay, so what we can do is we will first create the tree. We will apply that creation algorithm first, and then we will do the recursive traversals. If it is working fine, then we will write the stack class and then do the non-recursive traversal using that object of the stack class. Okay, so this will be the way of completing this program. Okay, now class tree node pointer root. We have done this for the simple binary tree as well. In the constructor, we are initializing root to null. Then we will be calling this create function, and in this create we will have the logic for creation of expression tree. This create is for creating the expression tree. Okay, from postfix or prefix. From postfix expression. Then we have a function root value which is just returning the root value. Okay, if we need, we are just reading that root value, so it is returning which is the root node. Then we have in order, pre-order, post-order recursive functions and non-recursive functions. Okay, in the recursive functions we are passing the root. Okay. Now we'll go to the create function and we will apply that particular algorithm which says when we are traversing the postfix string from left to right, we will be checking whether it is operand node or operator node. Okay, if it is operand, then we will create a node for that operand and we will push that node into the stack. If it is operator, we will pop two nodes from the stack. First popped node will be attached to right, secondly popped node will be attached to the left. Okay, this is the algorithm which we have seen. So see here, this ext is the expression postfix expression string which we will traverse from left to right. Okay, and these are the three nodes, temp1, temp2 and temp. Okay, for the operand or operator, the current character, we will need to create the node. Okay, so for that we have these three temporary nodes declared. Then we have created the object for stack. Okay, we'll go to the stack class and see, this stack is for node, it is not for integer, it is for nodes. Okay, and node is having the data of character type. Clear? So we are creating the stack of nodes. Node pointer data of 30. I have told you in the first practical turn to do this much. Isn't it? Write the class stack using array implementation. So this is array implementation of stack. Okay, we have allocated memory in the array to store the data elements, and our data is of type node pointer. Okay, we are storing the nodes into this. Then int top, as we know, every stack can be accessed using top. Okay, so these are the data. Hello. Yes. In the first turn, we have discussed that this you have to implement. Okay. We have already seen stack implementation using array in the last semester. Okay. But we have not implemented it. The data of 30 elements, that is 30 nodes it can store, and in top. So top is initially -1, as this is array implementation. Okay, top is initially -1, and we will go on incrementing the top when we are pushing the nodes into it. Okay. So in the constructor, top is -1. To check whether the stack is empty or not, we have this function. If top is -1, it will return yes, true. Okay, so 1. In the push function, we have to increment the top, and at that incremented index, we will be copying the current node which we have to push. So if we have to push this node P, then data of plus plus top is equal to P. So top will be first incremented as it is pre-incrementation, and at that incremented top position, we are writing the node P. Then we have pop function where the top data of top will be returned, and then top will be decremented. That's why it is the post decrementation. Okay, yeah. We will return data of top, and then top will be decremented. Okay, so simple statement, return statement is written into it. Clear? Is this implementation of stack clear to everyone? We have already discussed this array implementation of stack in the last semester. We have seen the stack editing. Okay, so we have written this stack class using array implementation, and for nodes it will be able to store the nodes. Okay, data is of the type node pointer, and we have written constructor is empty, push pop function into it. Is full is not required because we are assuming that there will not be more than 30 characters in the postfix string. Okay, so we have not written. If we want, we can write that is full function also, like is empty. Okay, so we will use this stack object in creation also. We have seen the create algorithm. We need to store the nodes into the stack. Okay, so in the create function, we are first taking the postfix expression from the user. Okay, this stack object S is there, which is stack of nodes. And after taking the expression, we are accessing that expression from left to right. Okay, so from I equal to 0 to expression of I not equal to /0. Okay, that means we are accessing the expression from left to right. And that current character, it is stored in CH. So CH is equal to expression of I, current character in the postfix string. Okay, and we will check using isOlnum function. We have already used this isOlnum function in the last semester also. This will check whether the current character is alphabet or number. So if it is alphabet number, then that means it is operand. Okay, otherwise it will be operator. So if isOlnum of CH, okay, it is uh, other than 0, not equal to 0, then a new node will be created, and in that new node the data ch will be copied at the data part. Okay, and that node will be pushed into the stack. Clear? So for operand, this condition is true for operand. When it is operand, the operand will be pushed into the stack. Okay, if it is not operand, that means it is operator. If it goes in else part, it is operator. This algorithm, all these conditions are similar to evaluation algorithm which we have implemented in the last semester. Okay, we are checking for operand and we are checking for operator. Operand is there, we are pushing it. If operator is there, we will pop two nodes from the stack. So temp2 is the firstly popped node and temp2 is next pop node. Okay, so temp2 will be attached to the left, temp2 will be attached to the right, first pop will be attached to the right, and temp1 will be attached to the left of the current node. And for the current node, we will create a node. For current character ch, we will create a node for it. Okay, so temp is the node holding the operator, current operator. And to this operator node, we are attaching the left and right nodes, these temp1 and temp2 nodes, okay, which are popped from the stack. Temp2, which is popped first, it is attached to the right. And temp1, which is popped next, that is attached to the left. Okay, so our operator node is now created and it will be pushed into the stack again. We have to push that operator node again into the stack. Okay, this will continue till we end with the expression. Okay, till we have the characters in our expression, we will check whether it is operand character or operator. Operand hai to we have to create the node and push it into the stack. Operator hai to you have to pop twice. Okay, firstly popped will be attached to the right of the current node and next popped will be attached to the left, and such node will be again pushed into the stack. Okay, and after this complete algorithm, this complete while loop, it is executed. That means we reach to the end of the expression. Then we have to pop once, and that popped node is nothing but our root. Okay, that popped node is nothing but our root. So our root will be initialized here. And once that root is initialized by the create function, so our create function, it is initializing our root. Okay, and that root is passed for the traversal here in order, pre-order, post-order, etc. Once the root is completely created, properly created, okay, we can use that root for traversal. Okay, is this algorithm? Okay, we can see the example of creation again, which we have already discussed in the morning. I'll just open that example and share. I'll just share that example. Opening. Do you have any doubt? Is that time just? Tell me whether this algorithm is clear, the method is clear. Refer our expression evaluation algorithms, which we have implemented in the stack assignment last semester. The conditions are similar to that. But here we want to create the expression tree. That's why we are creating the nodes and pushing the nodes. In the evaluation algorithm, we were taking the value from the user and we are inserting those values in the stack. Okay. Is this example visible? Yes, we have seen this in the morning also. What we were doing for this expression, if I want to create the tree for this postfix expression, I will access it from left to right. Okay, and when I'll access the operand node, I will create the node for it. Okay, this is just a simple character. I will create a node for this particular value a, and I will push that node into this node stack. Then b, for that I will create a node, push into the stack. Then when plus comes, I have to pop twice. Firstly popped this b node, it will be attached to the right of plus node, and a node, it will be attached to the left of the this plus node. Okay, and such plus node will be pushed into the stack again. Again, go ahead, access uh, next characters. They are operand c, d, e, so they will be pushed when the operator comes. Okay, plus operator comes, we have to pop twice and create the subtree for that and push the root of that subtree into the stack. This plus will be pushed again with d and a attached to the left and right. Then next is multiplication. Okay. So when multiplication comes, we will be, that is operator. So this plus node will be popped and it will be attached to the right of multiplication. And C will be popped, it will be attached to the left. So thus that subtree's root will be pushed into the stack. This multiplication will be pushed into the stack. And again we will pop another multiplication operator. So pop will be done twice. This subtree will be attached to the right. This subtree will be attached to the left. And such tree will be created that root of that subtree will be again pushed into the stack. And we reach slash 0, that's why whatever we pop here, this will be the new root. Okay, this will be the new root of the our root of the tree. Clear? This is the root, this is the tree which we have created using the algorithm. Any doubt in this expression tree creation? Can you relate now the example and the code, and then you can traverse using the same recursive methods first and then non-recursive. So after this tree is created using create function, we will use the in order, pre-order, and post-order traversal. We'll go to the main function. We'll see what is happening here. So in this main function, we are creating the tree object T1. Okay. So T1 dot create. Okay. T1 dot create will be created first, and then we have declared here node pointer root1 in order to have root value. So this function T1 dot root value, it will return the root node. Okay, so that we can pass this root node to the recursive functions, or we can also use the similar methodology that we used in the last turn. Okay, for binary tree, we what we did is we had some recursive counterparts. Okay, and we were calling those recursive functions in our functions which we are calling with object, isn't it? So you can use that method or you can use this method. Okay, here we are obtaining the root and we are passing that root to the recursive functions. Okay, both the methods are okay. You can use any of the methods for recursive functions, but recursive function needs a root access to the root function, which will be passed initially to the first recursive call. Okay, so these will be called recursive functions. Will be called. See these recursive functions definitions. We have already done this in the binary tree. Okay, which I have told you to do first. So this is the base condition. When t reaches null, we have to stop. Otherwise, in order, we will be calling first in order, then we will visit the root node and then the right. Okay, in order for the right. This is when in order of left subtree is complete, then only we will display the root, and then we will move to the right subtree like that. Okay, and for every node, this will be followed. Pre-order, first root will be visited, and then left subtree, then right subtree, and this is done for each and every node of that particular tree. In post order, we will visit left subtree, then right subtree, and then the root node. Okay, so all these recursive algorithms are clear. And what is happening besides that also we have discussed. Okay, so when tree creation and recursive traversals are working fine, then we can move to the non-recursive traversal. And as we discussed in the lecture also, for non-recursive traversals, we need stack object. Okay, because in the recursive at the backend, stack is only used. Why we need stack? Yes, why we need stack? If we have to traverse the tree. Why there is need of stack for traversing? Yes, involve in the discussion, interact, answer. Only few students they are responding. It should not happen. Yes, why we need the stack for traversal purpose? I'm asking the similar questions, nothing else. Yes, Chirag, can you answer? What is the need of stack? Yes, What is the need of stack?
Hello, ma'am.
Yes.
Ma'am, to store the values.
But why we need to store the values? Yes. Why we need to store the values?
Ma'am, demand a program.
But why only stack? Why not queue?
Ma'am, stack is more efficient.
And don't answer like this. Every data structure is efficient. There is no meaning for efficiency. Every data structure is efficient.
Yes, ma'am.
Then don't give the vague answers. When we use a stack, when do we use the stack and when do we use the queue? All both these data structures are for holding the data members or for waiting, isn't it? They are
Yes, ma'am.
holding the data members for some time. Then when we are using
Yes, ma'am.
stack and when we are using queue, what is the most important application of stack? Yes, stack is used when we want the data members in the reverse order. Okay, recursion is also doing that thing. Whenever the reverse order is expected, we go for stack. And whenever same order is expected of data elements entering in the queue, okay, we use queue. Okay, and why here we need the data elements in the reverse order? We'll see one example. That's why I am telling you, uh, work on these programs by your own, starting with the simple binary tree program. Then only you will understand the methodology used for recursion and non-recursion. Okay, we'll go to the same example. Okay, so for this tree, suppose I have to traverse this tree. Is it visible? I have to traverse this tree, and it is now root. I have only access to root node. So I can display that. If I'm doing suppose traversal in pre-order way, I can only display the pre plus. But when I move to left, okay, left subtree, my right subtree is still pending, isn't it? And that can be accessed through root only. So I need to come back after visiting the left subtree. I need to come back to the root again in order to move to right subtree, isn't it? So I need to come back to this root node plus after visiting left subtree. That means I will need the reference to this plus node afterwards. So I will hold this root in the stack for some time. Okay, because see I have the link from this root node to child node, left child node, but the reverse is not available. I cannot move from this child node to parent again because such link is not there. We have seen the node structure. In the parent node structure, we have the reference to the left child. But here in this node, we don't have reference to the parent node. So how we will go back to that parent? Okay, and I have to go back to the parent after visiting this left subtree. I have to go back to the parent and then move to the right child. Clear? So I will be holding this node, parent node, for some time in the stack. Okay. Then when this left plus node, left child plus node, this is visited, I will be moving to A, and there is no way to come back to this root of this subtree again. So I will be holding this plus also into the stack. And why in the stack? Because I will be reaching to the parent only. From A, I will be moving to this plus, and then I will be visiting the right subtree of this plus, that is this multiplication subtree. Okay, and until this is over, this part is completely over, I cannot move to the root of this complete tree, this plus. Okay, that's why stack. That means I will be accessing or visiting the immediate parent first before I visit the grandparent. So in the reverse order, I have to go back. I have started with this root, then I have came to the left subtree root, and then I have come to A. But I have to move to the current parent, immediate parent first. Okay, so in the reverse order, I have to go. Is it clear? Is it clear? That's why I need to store these nodes for some time in the stack. And why stack is used? Because its reverse order is expected. Remember our factorial function. In order to complete the 5 factorial, you have to complete the 4 factorial. And in order to complete 4 factorial, you have to complete the call for 3 factorial. So you are moving in the reverse direction. Okay, so calling is done in some way, and exactly in the reverse way, we are completing the execution. Okay, calls are completely executed in the exactly reverse order. Are you getting why stack? And all these questions are asked during the interviews, during your uh, examinations, whatever examinations, competitive examinations you appear for. All these questions will be asked. It is not efficiency every time, and efficiency is uh, nothing. There are parameters associated with the efficiency. Okay, only efficient data structure. It is not like then every for every application stack will be used. No, if a stack is efficient, it is, that is not like that. Depending on the application, we select which data structure is to be used. Mm. So we'll go to the algorithm for non-recursive traversal. Try to understand this algorithm. So in the recursion, whatever way is followed, similar way we have to write by using our own stack. Here, the implicit stack is getting used. In the recursive traversals, implicit stack is getting utilized in order to perform the recursion. And in non-recursive function, we have to write our own stack. We have to use our own stack object. This stack S is the object of the same stack which we have used for creation purpose. And we start the traversal from root. Okay, so T is nothing but a current node. Node pointer T is the current node which is initially root. Okay. And how in order works, we have to move to left. After visiting left, then root, and then right. For that left subtree also, root, left, and right. In this way only we work. So we start the in order traversal from the leftmost. So this while loop will take us to the leftmost node of the sub our tree. from where we have to start visiting. Okay, this will take us to the leftmost node of the subtree. While t is not equal to null, we will push the node into the stack. Okay, to push the node into the stack. Why to push? Because it will be now waiting. That node will be hold into the stack for some time, and then we are moving to the left. We are keeping the reference of that node, previous node, parent node, and then we are moving to the left child. Okay, so this loop will take us to the leftmost child. I will just share the screen so that we can simultaneously see the tree and the code. Are you now able to see the tree as well as the traversal program? So here what we are doing, this first while loop, it is taking us to the leftmost node, that is A. And while moving to A, we have pushed into the stack this plus node as well as this plus node. Okay, both the nodes we are pushing into the stack, and then we are moving to left. Also we have pushed A also in the stack, because until T is not null, we are pushing the node and moving to left. Okay, so we are now to the A left, which is null. At that point we are. And in the stack we have plus, plus and A node. These three nodes are there. Now, while stack is not empty, in our case also stack is not empty, T is equal to S dot pop. So first A will be popped from the stack, because we are now getting the elements in the reverse order from stack. It is last in first out. So A will be popped first. Then we will display A. We want that only. In order traversal, we have to display A first. So A will be displayed, that means it is visited. Then we will be moving to the right of the current node. So A right, which is again null. Okay, it is again null. So while T is not equal to null, again we are moving to left subtree of it. But T is null now. So what will be done? T is null now. So again it will come here and it will pop one more node. That means plus will be popped. This plus will be popped from the stack. And then it will be displayed, and we will move to the right of the plus node. That is this multiplication node. We will move to the right of this plus node, that is multiplication node. Clear? And why this while loop is there? It will again take us to the leftmost node of the current subtree, right subtree. Okay, so here in order to visit this subtree of multiplication, okay, I have to visit this subtree. I will be first moving to the left of most of the subtree, that is B. Then I will visit its parent, that is the multiplication, and then C, that is the right child. Isn't it? So when we will go to the right subtree, that is T equal to T right, first we have to move to the leftmost of that right subtree, that is B. Okay, so until we reach to the null, we have to push. So in the stack now we will have multiplication and B also. Okay, so in stack currently we have this plus. Okay, then we will have this multiplication, because plus is this plus is popped already, and then only we have moved to the right. Okay, so one plus node is there and one multiplication node is there in the stack, and B is there. Okay, B will also be pushed. Then B will be again popped. Okay, using this B will be popped, and we will move to right of B. It is also null. Okay, that's why one more pop operation will take place, and multiplication will be popped. This node will be popped, and then we will move to right. Okay. After popping, we are moving right. And after pushing, we are moving to left. Is this sequence clear? After pushing the node, we are moving to the left sub. After popping the node, we are marking it as visited and moving to the right sub. Any doubt in the algorithm? How to traverse the tree? And why stack is used? Because we need to access the nodes in the reverse order. Okay, we have to visit the current parent and then the grandparent, like that. Okay, any doubt? So here, for this tree, try to write the complete stack contents. Can you do this? For this, can you tell me what will be the stack contents in the sequential way? How the stack is it is changing? How the stack contents are getting modified? Can you do that? For this tree, can you write the stack contents till end? Have you completed? Tell me the stack contents initially. We will start from plus, and when see we are doing the in order traversal. In order traversal, we want to write the stack contents. So our stack is suppose S. Here we are storing the elements. Okay. So initially stack is empty. We start from root. We start from root and we will insert that root plus. Then then we will is after plus again the left subtree root that will be pushed into the stack, that is plus. Then A will be pushed into the stack. Okay. And when we reach null, we start popping. After we reach to null, we start popping. So A will be popped first, it will be displayed. After popping, we are displaying. So I will write the output here. Okay. After popping, we are displaying and moving to right. Right of A. So right of A is multiplication. Share the screen. Mm, Is it visible? In order traversal, see we are doing it for this example. So plus will be pushed, A will be pushed, and that will be done with the first while loop, which will take us to the leftmost node. Okay, so in the stack we have plus A. Okay, and when we reach the null, we start popping. So A will be popped first, and it will be displayed. The next is we will move to right of A, but that is also null. Okay, so we will pop again. This plus will be popped again and it will be displayed. After popping, we have to display it. Okay, and we will move to right of this plus, which is multiplication. Right of plus, this plus, which is multiplication, and that will be again pushed into the stack. So now our stack contains this plus sign, plus node, and we have one more node which is multiplication node. Okay, these two nodes are there in the stack now. At this stage, when we are at this node plus, then we will move to leftmost of this subtree, that is B. So B will again be pushed into the stack. Okay, and B left is null. B left is null. Okay, so in the stack currently we have this when we are at B left. Now B left is null, that means we have reached the condition. So we will pop and we will display. So B will be displayed. A plus and then B. Then after popping we have displayed B. We will move to right of B. But right of B is null. So we will pop again. Plus will be popped again. And sorry, multiplication will be popped and it will be displayed. Okay, and we will move to right of multiplication, which is C. We will move to right of multiplication, which is C. And we will move to leftmost of this, but it is null. And we will pop C and display it. Okay, so C will be first pushed. So in the stack, now we have plus node. Okay, this is our root node. And multiplication is popped and it is pushed. Popped and displayed. So we have C now in the stack. Okay, C is there in the stack. But left of C is null. So C will be popped and it will be displayed. C will be popped and it will be displayed this way. Okay? And we will pop next because there is nothing to the right of C. So one more pop operation will take place and plus will also get displayed. Okay, plus will also get displayed. And in the stack, now we have nothing. Now we have nothing in the stack. Now we will move to right of this plus. After popping plus, we are moving to the right of plus and leftmost of this subtree. Again, we will follow the same algorithm. So all the nodes in this left path will be pushed into the stack. Multiplication plus multiplication D. All these will be pushed into the stack. Okay. So we have in our stack multiplication, then multiplication plus multiplication and D. All these will be pushed into the stack. And D left is null, so D will be popped and it will be displayed. After this, D will be displayed. Then move to right of D, it is null. Okay, so one more pop operation will take place, multiplication, and after popping, we are moving to right. So we are moving to E. Okay, multiplication is also popped and it will get displayed. Multiplication is also popped and get displayed. Then we are moving to the right of multiplication, which is E, and E will be pushed. In the stack now, we have these two nodes as it is, and we have E. This is the next version of this stack. Now, when we are at E, E left is null. So E will be popped, it will be displayed. Okay, E will be popped and it will get displayed. Then move to right of E. After popping, we are moving to right, but it is null. Okay, so pop the next node, which is plus. This plus will be popped and we are moving to right of it. After popping, we are displaying and moving to right. So plus will be popped. We are moving to right of plus. Okay. So in the current stack, we have this node only plus multiplication node is there only in the stack. Okay. And we are moving to right of plus, which is F. Okay. So F will be there in the stack. This is the next version of the stack. Left of F is null, so F will be popped and it will be displayed. F will be popped and it will be displayed. Okay, and we are moving to right of F, it is null. Okay, so next node will be popped, which is multiplication. It will be also displayed. Multiplication will be popped and it will be displayed. And we are moving to right of the multiplication node, which is G. So G will be pushed into the stack. Okay, G will be pushed into the stack. Then left of G is null, so G will be popped and displayed. Okay, moving to right of G, which is again null. So in the stack, we will have nothing at the end, and that's why we will stop. Okay, our stack will be empty when we move to right of G after popping. There is nothing. If you see here, there is nothing to the right of G, so we will stop the execution now. These are all the stack versions created. Okay, is it clear? Any doubt in understanding the in-order traversal? Just remember the condition. When we are pushing the node, we are moving to the left. Okay, or we can say that while moving to left, we are pushing the node, and after popping, we are moving to the right. Okay, after popping, we are visiting that node, that is displaying, and moving to right of it. Only these two things we are following in the algorithm. Okay. If we see the algorithm, we are doing the same. In order to start, we are moving to first left. leftmost, because in order starts with the leftmost, and while moving to left we are pushing the node. Then we start popping. When we reach leftmost, we start popping. After popping, we are displaying the data and moving to right. And in the right also, we have to move to leftmost of that right subtree. Okay, so same thing we are following again. If we reach leftmost, we are popping, we are visiting, and moving to right. Okay, so this is the non-recursive algorithm for in-order traversal. Any doubt till this? Do you have any doubt in this algorithm or example? Like this, you can also try think about the pre-order and post-order traversal and write the stack contents for that as well. Okay, so we will complete these algorithms in the lectures, and I want you to implement all this. Don't only listen to the things. Okay,